So in this video, we'll look at the speed of sound in fluids. And it turns out that the speed of sound in fluids is really related to the rate at which pressure waves propagate through the fluid. We know that, I'm sorry, scratch that last bit. So let's look at a property that we need to define before we look at the sound speed, and that is the bulk modulus of a material. We have already defined a quantity that describes the rate of the proportionality constant for shear as a function of strain rate. What we are going to look at now is the compressive bulk modulus, which means what if we compressed a piece of fluid from all sides using pressure, how much does it compress? And what is the proportionality between that compression, that reduction in volume, and the pressure that we applied? That is given by what is called the bulk modulus of compression, and that essentially is once again a proportionality constant between the applied pressure and the fractional volume, well, the volume strain, which is really the fractional change in volume over the volume. And we have a minus sign there because we assume that if you took a cube, let us say, of fluid and you compressed it, it's assumed that compressive pressure is positive, the volume change is likely to be negative, so we want to keep this property positive, and so we stick in a minus sign there. Okay, so what does this quantity look like in practice? It depends on whether we are talking about a liquid or a gas. If we took a liquid, say water, and we wanted to create a change in volume by applying pressure, we would have to go to humongous values of pressure. So, for example, if we looked at the percent change in volume for water, which is dV by V into 100, and we are applying pressure and checking to see when we get a reasonable change in volume. It turns out that for water, you have to go to something like 450 atmospheres, 450 bar, before you see a 1% change in volume. That's the change in volume. The actual volume would be less than the initial volume. So we are just plotting the magnitude of the change in volume. So what this suggests is that water is practically incompressible. For most real engineering situations, you are not going to go to such high pressures, and so you can pretty much assume that that water is an incompressible substance. But if we did go ahead and calculate this E sub V, we would find that it is very, very large. So that's for liquids, where we essentially say rho is approximately constant. Not so for gases, obviously. We know that for gases at constant temperature, the increase in pressure would lead to a reduction in volume. But how it does that is dependent on the path that we follow. Okay, so we know that an ideal gas obviously is not incompressible. An ideal gas follows the relation P equals rho RT, that's the equation of state. And so for constant temperature, if I applied a pressure, then my density would change accordingly. In fact, at constant temperature, we would have P1 over rho 1 equals P2 over rho 2 for any process. And so if I wanted to find the bulk modulus of elasticity, bulk modulus, the compressive modulus, sorry. So it depends on the path I follow. I would have, for an isothermal process, I would have P over rho is a constant, and for an adiabatic process, as you have studied in thermo, P over rho to the gamma is a constant. So if I now calculate the compressive modulus for a gas, depending on the process, I'll get different values. So E sub V is defined as dP over minus d rho over rho for the gas process, and depending on whether it's adiabatic or isothermal, you can use these relationships to get two values. You'll find when you differentiate, when you plug in dP d rho from this expression, you will find that in one case, for an adiabatic process, you get gamma P, and in the other case, you just get isothermal. For an isothermal process, you just get the pressure. And this gamma there, if you recall from thermo, that gamma is the ratio of specific heats at constant volume and constant pressure. So you get two different values. And the definition of sound speed comes from the bulk modulus in the following way. When we hear sound, what we are really feeling in our ear canal is the frequency of waves of pressure that of air. Essentially, air is getting compressed and expanded as a sound wave travels through that medium, and that compression and expansion is what we feel. So the speed at which that wave travels is the speed of sound, and the speed at which that wave travels depends, it can be shown to be related to the bulk modulus. So now for an ideal gas, we have two choices to calculate the sound speed. We can either assume isothermal or adiabatic or something in between really, but let's stick to these two choices. Earlier, people used to think that because, well, the temperature of the air doesn't really change when sound's traveling through it, that an isothermal expansion, the isothermal assumption was the correct way to go, and so it was assumed that speed of sound is equal to square root of P over rho, because E sub V was assumed to be for an isothermal process, and using the ideal gas law, this would become square root of R times T. But this didn't really match with experiments, and it was determined that, and there were a whole bunch of theoretical arguments proposed to explain why it should be assumed to be an adiabatic process. So if you assume that sound travels, the process of compression and expansion of air as a sound wave travels through it, if you assume that's an adiabatic process, then you get square root of gamma RT, and this matches pretty closely with what we observe. For air, which is essentially a diatomic gas, gamma is 1.4, and at room temperature T of 300 Kelvin, we can show that speed of sound is approximately 340 meters per second.